Hello, this is Mr. Gilmore with the 1.3 angles lesson. We are going to look at angles from the same standpoint as if we were looking at the standpoint from segments like we saw in 1.2. So let's go ahead and jump right into what is an angle. We need to give a definition to what an angle is. An angle is a pair of rays with a common endpoint. Now, these rays that are used to form an angle, we're going to give a name to those. We're going to call those the sides of an angle. Now, this common endpoint that these two rays share, we also want to give a name to them as well. So we're going to give that common endpoint what we call the vertex of an angle. So instead of just breaking the angle down into rays and a common endpoint, we're going to give this specific jargon that says, hey, let's call those rays sides. So if I were to ask what's the sides of an angle, I'm really asking what are the rays? And whenever I say what's the vertex of an angle, I'm really asking what is the common endpoint? Take a look at the example down below. We see that there are two rays produced from point G. Now, these two rays, ray GF and ray GH, we would call the sides of our angle. And then since G is the common endpoint, we call that the vertex. Now, in order to name an angle, we're going to use a three-letter formatting. So when we see an angle, such like the example here below, we're going to use the three letters that we see as part of making this angle up. All right, of course, we've got the common endpoint, which has a letter, right, it's a point. And of course, we have a point on each of the rays because we had to name the ray. Now, what goes in these three blanks? The first thing we fill in is the easiest. We fill in the very middle blank with the vertex. So whatever the common endpoint, in our case, G will go in the very middle of naming this angle. What do we do then with F and H? Those come along the side. Basically, they flank the letter G on either side. So some valid names for this angle would be angle FGH or angle HGF. Any other combination of those letters would not work, right? I could not say this is angle GFH. Nope. I can't say angle HFG. Nope. I'd have to say angle FGH or HGF. G must be in the middle. So think of that common endpoint being the center of your angle name. Now, of course, we're not limited to just using the three-letter angle name. There's actually a couple other ways we can actually name an angle. If, in this case, we have two rays that are produced from the same endpoint, we can simply use a single letter name. So we can just call this angle G. Now we've got to be careful with angles like this, where we name it with just a single letter. So we want to be very careful because in this case, yes, it works. We have two rays produced from the same endpoint, meaning that we can name this just simply angle G. However, what if I were to put a third ray in there? If I were to say, hey, take a look at angle G, well, the third ray being in there, that does throw some ambiguity. Which angle am I talking about? Am I talking about this angle G? Am I talking about this angle G? Am I talking about the entire angle G, right? There's some ambiguity, which means we've got to make sure we're specific in naming our angles. So in cases where you only have two rays from the same endpoint, then you can use a single letter. But if there's a third ray or another sort of intersection there, you got to be using the three-letter name. Now, there is another easier way to name an angle, and that's simply to tuck a number into the mouth of an angle. So there you will see some cases where angles will be labeled with a number instead of using the three-letter name. So if you see an example below, we actually have two angles here, RZS and TZS. These two angles have a number tucked into the mouth of them. So angle 1 is the same as if I was looking at angle RZS, and angle 2 is the same as if I was looking at angle SZT. Now, those numbers that we tuck in are representing the name of the angle. Be careful, it does not represent the measure of the angle. I'm not saying that the measure of that angle is 1 and the measure of the angle is 2. Those are simply names. Now, let's talk about the measure of an angle. Imagine taking a single ray and rotating that ray about its endpoint, basically making a complete revolution with that one ray. Well, that ray, as it sweeps in that one revolution, imagine as it's going around that it completes 360 little parts. Basically, we cut that full revolution into 360 tiny little slices. Each slice of those we call a degree. So a degree represents one out of 360 slices of a complete revolution, which means when we encounter an angle, we can give an angle its measure by taking from one ray, sweeping over to the other ray. We can then think of how many of those tiny slices did it cover. That means we can give the angle a measure or a degree. So let's take a look at an example of an angle measure. Here's an illustration of a ray sweeping from one to another. So we have ray AB sweeping over to ray AC. Well, again, the count is how many of those little degree slices did it move. If we say that it took 120 of those degree slices, then we, by definition, can say that this angle CBA, has a degree measure of 120 degrees. Now we've also got to be careful with angle measure because technically we could have swept in either direction. Why did I choose to go from A, B in a counterclockwise direction? I easily could have chosen to go in a clockwise direction. So technically when we look at an angle really does have two angle measures to it. It just depends on which direction we sweep it in. Which one then will we choose? We're going to narrow down to the smaller of the two angles. So that's the one we're going to choose, and that's the one that we're going to stick with most often, unless otherwise specified. So just be careful with not always just jumping to, oh, let's look at both angle measures. Let's just stick with the smaller angle measure for now. Now, let's say I give you an angle and I want you to know what the measure of that angle is. How can I let the reader know where the measure of that angle is? I can tuck the degree measure of that angle into the mouth. So you want to be very careful to distinguish whether the number inside the mouth of the angle is the name of the angle, like we saw earlier, like angle 1 and angle 2, or rather it could be the measure of the angle. So in this case, I have an angle of 28 degrees. So watch for that degree marker, which denotes the unit of that measure. Now, when we talk about the measure of an angle, one quick note. If we write that out symbolically, we put a little m in front of the angle name. So that m represents the measure of. So when I read this sentence, or read this equation, it really reads as the measure of angle A equals 28 degrees. Hash marks. We see hash marks that come up again. We saw hash marks denoting equality with segments. We're going to see hash marks again denoting the equality of angles. So in our diagram below, you see that we actually have two pairs of equal angles. Remember, hash marks tell a story. They tell the story of equality. So if I look at the diagram, I see angles BAC, which has a single hash mark on it, and angle DAC, which has another single hash mark on it. What that tells the reader, what that even tells me, is that those two angles are equal. We have a second pair of equal angles because I see there's a double hash mark placed on each of these two angles. Now, here's a challenging question. So we know for a fact that based on our diagram that we have these two pairs of equal angles. Now, my question to you is, what if I am comparing two angles in this diagram, such the measure of angle BAC. Now treat this equation, this equal sign, more of like a question. Is it equal to the measure of angle, let's say EAB? Now, BAC has a single hash mark. EAB has a double hash mark. What do hash marks say? They only say one thing. They say things are equal. They don't necessarily say things are not equal. That's not what they can do. They can only say things are equal. So let's talk about this question. The question is, are these two angles equal? Well, if you said no, then you're wrong. But if you said yes, you're also wrong. We simply do not have enough information. When we do not have enough information, we arrive to this conclusion, CBD, cannot be determined. That's going to be our answer we see when we simply do not know what the question, or simply do not know have enough information to answer the question at hand. So the thing is, you may be looking at this diagram thinking, wait a minute, it looks like EAB is greater than the measure of BAC, but we don't really know that. Okay, diagrams are simply meant to give us some sort of uh, perception of what we are working with, but they don't hold the truth in them, right? We don't actually see that EAB really is greater. We don't know that. And so we're breaking the mold there of not basing things on how we perceive them with our eyes, but rather what is the truth that the diagram does hold. Because the diagram does hold some truth, and that has been marked with those hashes already. So just watch for that, okay? We're going to talk a lot about those assumptions that we can and cannot make. And just because it looks like it doesn't mean that it is, all right? So we cannot use what it looks like as a justification. Our last slide is the definition of an angle bisector. So say we're given any angle. Now I'm going to make a pretty bold statement here. Say we're given any angle. I am going to claim, and I actually can back the statement up later, that every angle has an angle bisector. That's a pretty bold statement. We'll talk about the reasoning behind that statement later. But here's what an angle bisector is. It's simply a ray that passes through the interior of an angle such that it splits the angle into a pair of equal subangles. So we have a diagram, an example down below. We're given angle ABC. Well, what we have then is a ray BP, that cuts through the interior of our angle. You also notice that we're making good use of our hash marks. Not only is it cutting through the interior angle, but we've labeled in our diagram that these two angles produced, ABP and PBC, are equal in measure. And so we can define then ray BP as an angle bisector. That is the ray that passes through that angle. So with it, that is the end of this lesson 1.3 on angles. If you do have any questions about it, please do not hesitate to email me, get in contact with me somehow. Other than that, that is really all there are to angles. We'll explore some other angle relationships in future lessons. We'll talk more about angles as we encounter them throughout the year. With that, be good and do good.